Today we're talking about simplifying radicals, and you can see in these examples here that we have both square roots and cubed roots. And so in order to simplify them, we need to think about values that are perfect squares and perfect cubes. So right up here at the top of the page, I'm going to squeeze in the margin a small list of perfect squares and perfect cubes, because we will need that information when we are going to be factoring our values to simplify these problems. Okay, so perfect squares are, you can think of our integers, our counting numbers, and squaring each one and writing down the result. So think of your counting numbers, 1, 2, 3, 4, 5, and square each of them. So 1 squared means 1 times 1. Right? 2 squared means 2 times 2, so that gives us 4. 3 squared means 3 times 3, that's 9. And so we'll do this. There's 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. We could keep on going, but I think those are the range of values that we're likely to see in the exercise today. So perfect cubes means we're going to go through those counting numbers again, but this time we're going to cube each one. So raise it to the power of 3. So 1 cubed means 1 times 1 times 1. Right? 2 cubed means 2 times 2 times 2. And again, we'll go through this. So 3 cubed is 3 times 3 times 3. That gives us 27. 4 cubed is 64, and just one more, 5 cubed is 125. Again, we could go further, but for our exercise today, that's, I think, the range that we need, and that's what we will be working with. Now, there is a technicality, because I had said we go through our counting numbers, and that's not quite accurate. We really want to consider all of the integers, both positive and negative. So if you go back to your perfect squares, and we go through our negative values, let's see if we can square those. So let's take a negative 1 squared. So that's negative 1 times negative 1. Well, that's a positive 1, so you get the same result. A negative 2 squared means negative 2 times negative 2. That gives you a positive 4. So you get the same result whether you are squaring positive integers or negative integers. When you think about that with the negative integers for cubing, we're going to take a negative 1, raise it to the power of 3, so that's negative 1 times negative 1 times negative 1, and that gets you a negative result. So that means you have to consider both positive and negative versions, because you could be cubing a positive integer or you could be cubing a negative integer. Again, if you had a negative 2 and you cubed it, that'd be negative 2 times negative 2 times negative 2. You would get a negative 8 result. So for all of these, we have both a positive and a negative version. Now, in our work today, we are only using the positive values. We'll be using the negatives in a different instance, but I'm just bringing it up now. For the rules, we're looking at little mini examples, these sort of building blocks, starting off with rule number 1. Here is the square root of, and you can see that we're multiplying these bases together under the radical. As long as you're multiplying, you are allowed to split up those bases as if each base had its own radical. And the reason why that's important is because this communicates that you are allowed to take the square root of x when you're multiplying with other things. So in our examples, we are allowed to take the square root of 25 because we're multiplying it with other bases. Now, by way of contrast, if you had an addition sign instead, so here we have the square root of x plus y. You cannot take the square root of x. You cannot take the square root of y. This rule only works for multiplication. Then you could take the square root of those independent bases. Here you can't. Why? Because that radical is a grouping symbol, and it groups together these two, which means you don't have x by itself. You really have a binomial. You have to take the square root of the entire bundle. So this, as it's written, can't be simplified. So again, in our work today, we are only using rule number 1. We will only be dealing with multiplication, but in the future we'll encounter the addition or subtraction. So I'm making that distinction here. Here's another rule. You've seen this before. If you are taking the square root of something squared, you're checking to make sure that the power matches the index, right? So again, that value is called the index. So the square root is often invisible. We don't write that down, but we understand if it's invisible, it's an index of 2. The power matches the index, It's as if they cancel out and leave you with just the base to the power of 1. That is also true with the cubed root. So if you have the cubed root of something cubed, as long as the index matches the power, it's as if they cancel out, leaving you with that information inside. All right, so those are the basic building blocks. Let's look at our examples here. So when I go to problem number 1, we have the square root of 125 times n. We're going to focus on the values first and then the variables second. When we're starting off with the values, we want to take that 125 and factor it. Again, factors are values that are being multiplied together. So what times what equals 125. And we want at least one of our factors, if not both of them. We want one of our factors to come from this list of perfect squares, because then we can take the square root of it. Now, if we don't know what that factor is, you're totally fine just using your calculator, just guessing and checking, saying, okay, here's 125, I'm going to divide it by a number and see if it divides evenly. Start off with the biggest number and work smaller. That way you're looking for the largest possible answer. So well, I'm not typing that in right. Let me try that one more time. So you can see it does not divide evenly by 64, so that's not a factor. We can try 47, right? 125 divided by 47. That doesn't work either. So kind of work your way down the list. 125 divided by 36. Nope, that fails as well. 125 divided by 25. That one works. So that gets us an answer of exactly 5. So that's the factor pair, 25 times 5. So rewrite that as 25 times 5. And here we just have n to the first power, so it's just n to the first power. Nothing to do with that right now. Now, normally we do this next step in our heads, but I'm going to write down using this rule so you can see what we're doing in our heads. In our heads, we're taking the square root of 25 as if it were by itself. And then we'll take the square root of 5, and then we'll take the square root of n as if it were by itself. And this is a perfect square, so we can simplify this, and the square root of 25 gives us integer 5. But these other values are not perfect squares, so they are stuck under the radical, and we will group them together under the common radical. So that's your answer. So again, this step right here, we usually just do in our heads and write down the result of that. So we'll see a little bit more detail when we get to some bigger values. So let's go to problem 2. Again, it's a square root. So I'm thinking of factors of 216. Again, I don't know my factors of 216. You don't have to, right? Just use your calculator and divide using the list of perfect squares here so that we can see if we have perfect factors. So it is not divisible by 64. Working my way down the list, it turns out to be 36. All right, so it's 36 times 6. Now when we get to the variables, again, we want the power to match the index, and the index is 2. And you can see it does not match. We have a lot more. We have 5 powers of v. So we're going to take those 5 powers and rewrite them in bundles of 2. We want as many bundles of 2 as possible. So we're going to write that v to the power of 5 as v squared times v squared times v to the first. That's my 5 powers of v. Remember, when you are multiplying the same base, you add those exponents. So 2 plus 2 plus 1 does add up to the 5 that we started with. So that's a valid way to rewrite v to the power 5. We want that because we want as many of those powers to match the index of 2 as possible. So now instead of writing down this rule, we're just going to think it through in our head. Let's take the square root of the first thing, the square root of the second base, the square root of the third base, and keep on going right on through. So the square root of the first base, the square root of 36 is 6. The square root of the next base is just root 6. The square root of v squared is v. The square root of the next v squared is also v. And the square root of v to the power of 1 is root v. So we're pretty much done. We just have to reformat it so it looks good. Put your numbers in front. Those are your coefficients. Then group together the variables. So v times v is v squared. That'll be bundled up here. And push the radicals to the back. So root 6 times root v is radical 6v, and they share that common radical. So the rest of these are just variations on this same technique. Here's problem number 3. I want to find factors of 147. Again, I'm using my calculator to help me guess and check as I work my way down the list. That should be 49. I see that looks like a 47. What was going on? I don't know. 7 times 7 is 49. So if you caught that mistake, nice catch. So that should be a 49 right up there. And that applies here because we want these factors of 147, and that turns into 49 times 3. Okay, here we have m cubed, so let's rewrite that as m squared times m to the power of 1. So those are my 3 powers of m. Similarly, n squared times n to the first. Okay, let's take the square root of each of those. So we get square root of 49 is 7, square root of 3 is root 3, square root of m squared is m, square root of m to the first power is root m, square root of n squared is n, and square root of n to the first power is root n. And now let's clean it up. Bring your integer to the front. Next, bring the variables m and n, so m times n, and push the radicals to the back, and multiply 3 times m times n under that radical sign. So there's the final answer. When we're looking at number 4, the only real difference here is we have an integer out front. So what happens in a case like that? Well, it's just going to stay out front for a little bit, and eventually it'll get multiplied to whatever numbers show up next. So I need to find factors of 24. So what times what is 24? And we want numbers from that list of perfect squares. We want the 4. 4 times 6 is what we'll use. And take that k to the power of 5 and rewrite that as k squared times k to the first. That's my 5 powers of k. Again, that negative 8 is just hanging out front. Let's take the square root of 4. So that turns into a 2. What do we do with that 2? Are we adding it? Are we subtracting it? No, all of these are being multiplied. So that square root of 4 is the integer 2. And that later that'll get multiplied with the integer of negative 8. The square root of 6 remains root 6. The square root of k squared is k. The square root of the next k squared is also k. And the square root of k to the first power is root k. So to clean it up, put your integers out front. Then come the variables. So k times k is k squared. And push the radicals to the back. So root 6 times root k is root 6k. There you go. So those first 4 all use square roots. What's different now is that we are working with 2 examples that have cubed roots. So what that means for us is that when we are finding the factors inside, we want perfect cubes. So we need to go to our list of perfect cubes, there it is, and figure out what times what multiplies to 24. And these numbers are too big, right? So that would indicate we need an 8. So 8 times 3 is 24. And again, we're just using the positive version of 8. Don't worry about the negatives. That also means when we have powers, we want to redistribute those in bundles of 3 to match the index of 3. So a to the power of 4 will be rewritten as a cubed times a to the first. Now b squared, that's less than the index, so I cannot rebundle that as a power of 3. It just stays as b squared. And c cubed already matches, so again, it's already a bundle of 3, so we're good there. There's the negative 3 in front. Now let's take the cubed root of each of these. So the cubed root of 8 is 2. How do we know that? Right? Well, that's the second number on the list. We said that 2 to the power of 3 is 8. So when we go backwards, the cubed root of 8 results in that 2. So this is the first number, this is the second number, that's why we have 2 right there. The cubed root of 8 is 2. The cubed root of 3 is just cubed root of 3. The cubed root of a cubed is a. The cubed root of a is cubed root of a. The cubed root of b squared is cubed root of b squared. And the cubed root of c cubed is c. So in cleaning this up, we'll have our integer of negative 6 in front. We have the variable of a and c, it looks like, so a times c. And then we'll push the radicals to the back. So we have the cubed root of 3 times a times b squared. And there's our answer. Here's one more example with cubed roots. All right, so we want the cubed root of 64, and look at that, it's already on the list, so we don't even have to find the factors. It is the perfect cube to begin with. So I'll just leave it as is, there's 64. So let's take the j to the power 6 and reformat that in powers of 3. So there's j cubed, k to the power of 8 becomes k cubed, and k squared, because 3 plus 3 plus 2 adds up to 8 powers altogether. So let's take the cube root of 64, and that gives us an answer of 4. Again, how do we know that? Because it's the fourth number on the list, 1, 2, 3, 4. We got this by taking 4 and cubing it to get 64. So now we're taking the cube root of 64, and that results in 4. The cube root of j cubed is j. The next one is also j. The next one is k. The next one is k. And lastly, you have the cube root of k squared left over. So to clean it up, you have your integer in front. Multiply your variables back together again. So j times j is j squared. K times k is k squared. And push your radical to the back. So cubed root of k squared. Don't forget that little cubed root sign there in your answer. I find that sometimes my students will accidentally leave that out, and it looks like a square root, which is not correct. Make sure that you match the index there from the problem.